Hi, let's talk about VSEPR. Now this is going to be a part one. I split it in two. We're only going to do through 4 electron domains. I'm also going to give you the foundation in this video. So VSEPR stands for Valence Shell Electron Pair Repulsion. This name, that huge name, has the acronym VSEPR. And the name actually embeds the meaning. We can predict the shape of molecules based on the electrons that are around, I should say the electrons and atoms that are around the central atom. And here's the driving principle. Electrons repel each other. So if you have electron domains, electrons will always repel a maximum distance from one another. So let's pretend that I have this central atom right here, and I have 2 atoms attached to it. This would be considered an electron domain, that bond. This would be considered an electron domain. Now, notice 180 degrees. They are repelling a maximum distance. If one of these started to bend this way a little bit, the electrons would repel it and push it down. If it started to bend this way a little bit, the electrons would repel it and push it back up. So that's the driving principle. Electron domains, areas, regions where electrons exist, they repel each other maximum distance. And based on that, we can predict the shape of molecules. So let's look at some of the thoughts, the information that you need about this. So again, we can determine the shape based on electrons repelling a maximum distance. Next, I've used the term electron domain. An electron domain is anywhere where there's a density where electrons exist. So I just put area where electrons exist. Now what qualifies as an electron domain might be a little bit different than what you think. So a lone pair, that's when you have 2 electrons sitting on top of an atom. A single bond, that's an area where electrons exist. Likewise, a double bond and a triple bond are also considered electron domains. And not only that, they're considered one electron domain. And here's the reason why. It's still one area where electrons exist. If I have a single bond, there are 2 electrons that exist there. If I have a double bond, there's 4 electrons, but they're still in one area. So it's still considered one electron domain, even though there's more electrons in that area. It could be like one family has 4 people, but they live in their house. Another family has 7 people, but they live in their house. They're both family dwellings, even though there's a different amount of people that live in each house. Same thing, electron domain, area where electrons live, where they exist. Okay, so you can Google VSEPR tables. I'm going to help you read them and interpret what it means. So we have electron geometry. The electron geometry is based on all the electron domains. So this is going to be based on all electron domains, all areas where electrons exist. That will include lone pairs and the bonds. Next, molecular geometry. If we could actually look at the molecule, this is the shape you would see. And here's what you have to know. We can't see lone pairs. I can't see 2 electrons sitting on top of the atom. So this would be what the shape actually looks like. Shape looks like. Now, if you're asked, hey, what's the geometry? What's the shape of a molecule? They're asking for molecular geometry. They will have to specifically ask for electron geometry if that's what they want. It's inferred, assumed that when you're asked for shape, they always want what it looks like, understanding we can't see the lone pairs. So they're asking really for molecular geometry. So we're going to start with 2 electron domains. And here's my example for 2 electron domains. This is going to be my central atom. So in this case, I have a beryllium chloride, and you know, that's kind of a fudge. That's supposed to be more of an ionic compound than a covalent, but it gives us an example of a linear of 2 electron domains. So give me grace using this example. So beryllium in the center, single bond, 2 my chlorine atoms. Okay, these chlorines are going to repel each other. It's because of those 2 bonds, a maximum distance, which means their distance is 180 degrees. So look how we write that down. We've got 2, where it says total pairs and shared pairs, these are really going to be that I'm looking at the electron domains. So I would say this has got 2 electron domains. So I've got 2 total electron domains. Let me write this down here. This would be your electron domain. And then I qualify, I'm really specific. Well, 2 of those domains are bonded and there's no lone pairs on that central atom. You always look at the central atom. Let's write that down. Look at the central atom. That's always what we're looking at. And if I do this beryllium dichloride like that, the beryllium has no lone pairs. That's why the lone pairs are going to be 0 on that. Let me move that mouse. Okay, oops. Sorry about that. Hybridization, we'll come back to that, so you can watch the video on hybridization. So the shape, that's linear. That makes good sense. 180 degrees between the 2 electron domains is called linear. So there's your first one. Now, we're going to go to 3 electron domains, 1, 2, 3. So here's my first example, is an aluminum chloride, also more covalent than it is ionic, but it gives me an example. So aluminum is a central atom and has a single bond to each chlorine atom. So I count 1, 2, 3 total electron domains. So these are going to repel a maximum distance. You could probably see it repelling that maximum distance. That maximum distance is 120 degrees. So let's see how we wrote it. 3 total electron domains, 1, 2, 3. They're all bonding. There's no lone pairs. That central atom aluminum has no lone pairs. So this is called trigonoplanar. So triangle, and it's on one plane. It's on one plane. So there's the name. Now these names, try and make them make sense. For the most part, they can be reasonable, but you're memorizing them. So try and make it make sense of, oh yeah, 3 electron domains. It looks like a triangle if I were to connect the dots, and it exists on one plane. And so your angle on that is 120 degrees. Now, I wrote this one in. We're going to take a sulfur dioxide. So here it is. You'd have the sulfur in the middle, and you can draw the Lewis dot structure for this to see it. You'd have sulfur, double bonded oxygen, single bonded oxygen. If I count that around that central atom, I've got 1, 2, 3 electron domains. Remember that double bond still counts as 1 electron domain. So I got 3 electron domains. There's a double bond, there's a single bond, and there's the lone pair. So when I write this down, yeah, 3 electron domains, 2 are bonds, okay? 2 are bonded electron domains, even though 1 single, 1 double, great. And 1 is the lone pair. So the electron geometry, its shape is still going to be based off 1, 2, 3 electron domains. Electron geometry is still trigonoplanar. But what we see, remember, I can't see that. I can't see those lone pairs. So the shape right here, all we see is this part down here. The shape is actually called bent on this. It's bent, and we'd still say that that would be 120 degrees. In reality, it's a little bit closer, maybe like 118, because lone pairs sit close to the central atom and they torque and push and repel a little bit harder. But for what you need to know, 120 right there. Okay, so I wanted to add that one so you could see what happens when we add a lone pair to a trigonoplanar electron geometry. All right, let's go to the next one. So this is tetrahedral, 4. So here's my example of 4. Now I want to show you how we end up drawing this. If I take methane, we draw it very symmetrical with a lot of right angles. We do this: carbon, hydrogen, 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 hydrogen. It looks like 90 degrees. But in reality, this is it. And you can see that is not a plus sign. That is not a plus sign. To me, it looks like a tripod. That here, pretend that we have the stand with 1, 2, 3 legs, and then coming up here, this would be like where you would set your camera. It looks like a tripod to me. That is tetrahedral. So we draw it as a plus sign, 2-dimensional, but that's not how it exists in space. It's 3-dimensional. So let's look. We've got 1, 2, 3, 4 electron domains. They're all bonded. There's no lone pairs on that carbon, 0 lone pairs, and so it's called tetrahedral. Now the maximum distance that these two repel each other from here to here That is 109.5 degrees. 109.5. I joke that could be like a radio station. KK Chem 109.5. Listening to your best chemistry facts. Okay, so 109.5 maximum distance. Now let's change it up a little bit. We're going to add a lone pair. So here is ammonia. We have nitrogen has a lone pair and 3 single bonds each to the hydrogen. Let's count electron domains. 1, 2, 3, 4 electron domains. Here's what it would look like. I have a lone pair up top. So the electron geometry is still 4 electron domains. 1, 2, 3, 4. See? 1, 2, 3, 4. There we have it. So it's still tetrahedral. The shape is going to be forced by 4 electron domains. Let's look at this. 4 electron domains, 3 are bonds. 1, 2, 3. 1 lone pair right up top. And then the name and the angle are a little bit different. Remember, I can't see that top lone pair. I can't see this right here. All you see is the bottom triangle part, and this, like bottom of the tripod, it looks like a pyramid. And so it's called trigonal pyramidal. Trigonal pyramidal. And the angle, so again, lone pairs sit closer to the atom. They have a greater repelling power because they're closer to the atom. So they push and repel, that these actually come a little closer together. So this angle is slightly smaller, is 107 point, oh, this is 3. I've also seen 107.5 on that. So I'm going to do what I tell my students, 107.5 degrees. So it pushes down just a little bit more, 107.5. Okay, now we can change it again. Probably our most common molecular shapes that we'll see is water, right here, water, so you can see that. Let's do the electron dot. Our Lewis dot structure, okay, there's water. Oxygen shares an electron with the hydrogen, it has 2 lone pairs. So let's count electron domains. 1, 2, 3, 4 electron domains. 2 are bonded and 2 are lone pairs. So electron geometry, still tetrahedral. I still have 4 electron domains, but the molecular geometry, we only see, if we could look at this, you only see these 2 bonds. You can't see the 2 lone pairs right there. And so this shape is a little anticlimactic because these are cool names like tetrahedral and trigonal pyramidal. That for water is called bent. Yeah, there it is, bent. Now because there are 2 lone pairs sitting on this atom, you can see the 2 lone pairs, and those are really repelling, pushing, pushing, pushing. This angle is even smaller. It is 104.5, 104.5. All right, that a little bigger for you, 104.5. So there we have 2 electron domains, linear. 3 electron domains, trigonal planar. 4 electron domains, tetrahedral. And the options that we have inside of those when you have lone pairs on them. Now, if you need 5 electron domains or 6 electron domains, you can watch part 2 of VSEPR. Good work and have a nice day. Thanks.